Hi, everyone. Good afternoon, or whatever time of day you're calling in from. Welcome to day 4 of the OSG Virtual School. And today's topic is software, specifically backpacking with code, software portability for distributed high throughput computing. And we'll talk about a little bit about what that title means in just a second. But first, I want to give an overview of what I'll be covering today. So we'll start with a brief introduction to what we mean when we say making software portable and kind of what our goal is when it comes to getting software ready to run on a distributed high throughput computing system. Then we'll talk about some underlying concepts around software, how it works, how it's installed, and what implications that has for us in using a distributed high throughput computing system and making our software portable. And then finally, we'll talk about software portability techniques, how to actually do it, and give some ideas and templates. There'll be a short demo that I'll give somewhere in the middle, and I'll also pause then for questions. But at any point, feel free to put questions into the chat. The school staff are on this call and will chime in, and then if there's any kind of open questions or questions at the break, I'll answer those then. So let's dive in. So first, I'm going to use an analogy to introduce this idea of software portability. And so the initial analogy is that running software on your own computer is like cooking in your own kitchen, where you know what's there, whether that's ingredients or installed programs. You know where everything is for the most part, and you have control. You can reorganize, you can add things, you can make changes. Okay, so when we move into distributed high throughput computing, we meet this challenge, which is that we're using someone else's computer that's possibly shared. And so our analogy is that running on this shared computer is a little bit like going somewhere else and cooking in someone else's kitchen, where you may not know what's already either there or installed, the kitchen or the computer, and where you may not know where things are. Maybe, you know, this computer does have a copy of R, but you don't know where it is, the same way that your friend has a muffin pan, but it's in a weird location. And you're probably not allowed to change whatever you want, not if you still want to stay friends with the person that you're borrowing the kitchen from. Same thing with using someone else's computer. And so we have to keep these things in mind when using software on a system like the OSG. And so this is why we talk a lot about software portability, which means taking our software with us, installing it and running it, and sort of bringing it along, thinking like a backpacker, where you bring along the cooking equipment and the food you need. So here we're bringing along the software we need. And so when we talk about software portability, that's what we need. All right, so that's our goal, portable software. We're next going to talk about some concepts or ways of thinking about software that are going to be important for running on a distributed high throughput system, and for making our software portable, and like how some of these pieces fit together. So the first concept is that software is files. That's not how we commonly think about or interact with the programs we run, but in reality, every program or software you run on your computer is behind the scenes a file somewhere on the file system, in a format that your computer can execute. So for distributed high throughput computing, that's what we need to take along. We need to identify and isolate the specific software files we need and bring them with us to the execution server. Okay, thing number 2. So our program, as just stated, is a set of files. And I've included here some terms we and I may in this talk use interchangeably to talk about underlying software files, code, executable binary. And when we run programs, those files launch to a running program, sometimes called a process or instance, which sometimes depends on different software files runs its own tasks, interfaces with the operating system, and through the operating system can actually use the underlying hardware. So if this is how software actually runs and works, that has some implications for us for making it portable. Software depends on the operating system it was compiled to use and potentially other installed programs. So if we're running on a system like the OSG, we need to be able to run our programs need to be compatible with the target operating system, which is usually Linux, and we have to bring along other dependencies. So that's just an extension of that first principle. Those are some of the files we need to bring with us. Okay, so if software is files, we have to put them somewhere. So let's say this is a schematic of a Linux file system. The directories at the top are what are commonly called system locations. And at the bottom are what are called local locations. You can see they're user home directories. And so this is probably similar to what we would see on a server where we're going to run a job. And so our files have to go somewhere in here. Those top level folders aren't accessible to normal users. They're accessible to administrators, to people who run the servers. It's only the bottom set of folders that are available for a user where they can actually add new files and then use them. You can access files in these system directories, but you can't add to them. And we're bringing along our software. We need to be able to add. So we need something like this, like a local or user-specific folder in order to run our software. So software files have to go somewhere. Where they go has to be accessible, as in terms of we can actually add files to this location without administrative privileges. And then wherever we install, we need to know where it is and be able to access it. Okay. I think we're on principle number 4. This is not related to software portability so much, but just a large scale distributed system. We're submitting jobs, everything has to be automated. So we have to use the command line. And so if the program we're using has a GUI or graphical interface, we need to find the options to run it from the command line, or otherwise with a script or programmatically somehow. Multiple commands are okay, but it needs to be this sort of command line scripted text-based way of running a program. Okay, I think this is our last concept that's going to impact software portability, and that it puts the previous two together. So our software files have to go somewhere. We have to run our software from the command line. In order to do that, the command line, whatever we're using, needs to know where we put our software files. So there's different ways to do this. You can provide a path, either relative to your current directory or an absolute path from the top of the file system to reference a particular program. Or you can add the directory containing that program to the system path, represented here in all caps, the kind of standard variable. And so here we have the path is now going to equal to our custom software location, probably local, that we control. And then using the colon separator, appending the original contents of the path. And so if you print that out, you'll see that our folder with our copy of Python, say, has been added. So if we run the Python command, it'll use that copy because it will show up first. Okay. So that was a little bit of the how-to, but to reiterate, to run a command in a script, your computer has to be able to find it. And if you're using like a shell script approach, there's different ways to find your software, including providing the path or using the environment path variable. Okay, so putting all those pieces together, some things we have to think about to make software portable. We need to bring along all of the files we need that are Linux compatible, put them in a location we can access or control. This is going to be the jobs working directory. We have to tell our script or command line where those files are, probably in our working directory, and then use the command line to run our code. So now it's time for the demo. So I'm going to walk through some of these principles through this R example. I guess I closed the other window I had open. Okay, we'll make do with this. All right, so the first piece I'm going to illustrate is going from using a GUI graphic interface to the command line. So I'm on my own computer. I have an R script. I'm running it in RStudio, which on my own computer is a great way to work with R. And so there's a lot of ways I could run this script. I can kind of print out each line separately if I want using command shortcuts. I can highlight it and click the run button. But to run this script on a resource like the OSG, I need to run it from the command line. So let's do that. So I'm going to switch over to a terminal window where I'm in the folder that has my script. And so this step for R is pretty simple. And if you don't know if this is a transition you have to make with your program, this is the kind of thing where I Google, run X command line, and then see what pops up. So in this example, I can use the R script command to execute my script. So I'm going to type that and then the name of my script. Off we go. So that step was really simple. So I now have something that I can sort of execute on a system that's scheduled using jobs. Okay, so now, hopefully this works. Now I want to take what I just ran on my computer and run it on a high throughput system. So here I've started a job on a server. So it happens to be called Interactive 2000. And Condor, which is the scheduler we're using, has given me a working directory for the job. So you can see that's listed here. And I have my R script that I brought along with me. So first, I'll just try running the same command I ran on my computer. Okay, so this is not going to work because my R script, to the command I use to execute it, the R script command, isn't on this computer or isn't on a place that's sort of normally where it's installed. So I need to get a copy of the R script binary, the R script file, so I can run my script. So I have a kind of R installation pre-prepared that I'm going to grab really quickly. I think that's right. Yep. So it's zipped as a tar file, and I'm going to unzip it and then remove the zipped file. Oops. Okay. So for those of you who are like, where did that file come from? What's happening? That's part of what we'll talk about in the second half of the talk. So we'll talk a little more about how you actually get the files you need to run a particular software. But for now, I pre-prepared them. So I just downloaded, unzipped. And so now I have a folder called R. If I look in this folder, I have a couple subfolders, subdirectories. If I look specifically in this sequence of subfolders, this is a the components of a standard R installation. And if I searched through my computer, my own personal computer's file system, I would eventually come to a folder that looks like this, that has all these components in it. Of more direct interest to us, if I look at the bin subfolder, there I see the R script executable. So that's great. So now I brought along my R files. They're in a directory that I can control, which is the jobs working directory. So now I'm going to try to run. Okay, so this still didn't work because of, I think, the last point I made, which is that I have to tell the command line about the location of these files that I just downloaded, brought along. So I can do that by putting in the path like this. So that's the well, not full, relative path to the R script. And then it will run. Or I can take an environment path variable, which is path in all caps. I can add the path to my R bin folder. So I'm being a little sneaky here. I'm shortcutting the first chunk of the path using the PWD variable. So that'll print the full path to my current working directory, and then I'll add the pieces that I've added, which is the R folder and its subfolders, colon as my separator, and then $path to append the existing path variable, which is again a list of directories. So if I print this out, you'll see I now have this very long path to my R bin folder, and then all the folders that were originally part of the path variable. And now I can just, as I did on my own computer, type R script, simple.r, and it executes my code. So typically in a job, it wouldn't be doing this interactively. Instead, I'd have a script that unzips the tar file, maybe sets the path like this, and then runs my code. And we'll talk about that again in the second part of the lecture. There was a question earlier about packages. So this example just uses base R, but if my R code used additional packages, then those would also need to be pre-installed or installed as part of the job, brought along somehow so that they would be available for my code to run. And I've used R in this example. Python is very similar. A lot of kind of scripting languages, Python, Perl, Julia, I think, very similar. So this example could be extended to those as well. But yeah, that's an example of what it actually looks like to put together those principles of software and what they mean for distributed high throughput computing. Okay, so now basically the second half of this talk is different ways to prepare software files and then run them in jobs. So we're going to start with three examples that I think cover a wide variety of how most software works and is put together. So here's kind of two scenarios, ways that you could get software files. You could download them, or you could compile them yourself. And it may be in the format where you either download or compile a single binary file, or you download or compile kind of a self-contained installation. So that's what you saw in the demo I just did with R. So I'm going to take a short pause here to talk about compilation. So compilation is the process of turning source code, which is human written and human readable, which is all software starts this way, and compiling it into a format that a computer can understand. In this process, it incorporates information about the operating system it was compiled on. So this gets back to a previous question about, doesn't the program have to be compatible with the computer? The answer is yes, and this is part of the reason why. And there's a part of the compilation process where if the main code references sort of pre-existing libraries, sort of external functionality that are meant to be incorporated into the code, the default way that this happens is there's links added to the code so that when the code runs, it kind of refers back out to those external code libraries. So this actually can work just fine on the OSG. It does require that the libraries that your code may use are there and consistent, which if you're using the same operating system is generally the case. More about exception in a minute. So if you are compiling your code, so you can either download, but if you're compiling, you might be using a compiling tool like GCC directly. More frequently, software programs will have this 3-step process where you run a configuration script, a make step, which runs a lot of different compilation commands in the right order, and then some kind of installation command, which takes the compiled code and puts it sort of in a final location. So for both these options, there are ways that you can control how the compilation happens. You can either pass the commands directly to the compiler or potentially introduce them in the configuration step if you're compiling code that has this 3-step process. Okay, so why I bring this up, the reason for explaining this is that there are options, often either kind of method that was just described, to make that linking step of compilation into what's called static linking, where any external code in library files gets bundled into the final compiled binary file, so that when the code runs, it doesn't need those external library files to be present. It can just run on its own. And so this is just more portable. You aren't as dependent on some of the underlying files and installations on the computer. So that's one technique for making things more portable if you are building the code kind of from source yourself. Okay, so this can result in either a single static binary or a folder with a bunch of different components in it. Sort of as a subset of that second category, if you were running what's called interpreted code, so the demo I just did is an example of this. Our code is not compiled. I didn't compile my R script itself. Instead, I ran it through the R script interpreter. So that was the actual R script command that I ran. So a lot of scripting languages are like this. Programs written in C, C++, and Fortran are compiled. So they, like the process described a couple slides ago. For interpreted or scripted languages, you don't compile the scripts. However, you do use a compiled copy of the underlying interpreter. So if you're using Python, the actual Python program is compiled, and then you use it to run your uncompiled script. Same with R script and R script. So, so this is kind of another flavor of what your software files can look like to run a job. So here you'd have a compiled interpreter and your actual script. Okay, one more very specific example. I think of Matlab as a scripting language, like R or Python, but you can in fact compile it using a special Matlab compiling tool, and it converts it to a binary format that you can then run with another set of files called the Matlab runtime. And so those two together work a little bit like an interpreter and code that's being run through it. So the main reason that we use this approach locally at our center is that the compilation step requires a Matlab license, but then you can run as many copies of the compiled code as you want for free, using, because the Matlab runtime is free. So that's a great path for us. So hopefully, at least one of those examples resonated with you in your experience of working with software. Again, download or compile, and you'll end up with a binary or a whole folder installation or an interpreter. And those are the files that you need to bring along to run your job. Okay. So once you have the files, how do you actually use them in a job? So we'll do a couple slides on this. If you ended up with a single binary, you can put that binary file's name into the submit file as the executable, and it will run. So it's very straightforward. One option. If you have an interpreter or a whole kind of folder structure, or you just want to do more things in your job besides run the single binary, you can use a wrapper script shown here. So this is typically written in a shell language like Bash, where you can perform some setup steps for your software. So this is exactly what I did in the R demo. You know, I unzipped my R installation tarball, I set the path, and I ran my code. So that's exactly the kind of thing that goes into this script. And then that script becomes your executable. And any software or data components it uses get listed in transfer input files. So that's how you put these pieces together to run a job in sort of diagram form. If you have a single static binary that you either compiled or downloaded, that just gets shipped out to different execute nodes and run directly. If you have a wrapper script and then compiled code of some variety, an interpreter, a binary, a folder, these files get transferred. And then on the wrapper script is your executable. And so inside the job, the wrapper script sets up the software installation and then runs the desired command. Okay, so there's some steps here, but once these are set up, you know, the idea with compiling things in advance and then just running them is you go through that whole compiling process and get everything set up kind of one time. And then you can run hundreds, thousands, tens of thousands of jobs using that same setup. So the work of setting up your software, it's both needed, but it also has a big payoff in terms of being able to run a lot of computing. And making your software portable means you can run on more resources. You aren't confined to a certain subset of computers that you know have certain tools, or you know of this. It just gives you a lot of flexibility. So that's, again, that's the big picture goal here, is being able to run lots and lots of jobs on a lot of resources. And these are tools to get you there regarding software. Okay, so that was a sort of series of examples around software, really software files, binary, software folder, interpreter, whatever. And so one other way of assembling or putting together your software for use on other systems is containers. So we'll give kind of a short intro, very, very short intro to what containers are and why you might want to use them, and then how to use them on the OSG. So for folks who haven't heard of containers, they're a tool for capturing basically an entire file system environment. So software, a lot of the things I've just been talking about, software, libraries, sometimes specific versions of Linux. So that all gets captured and sort of put into an image, which is a file that can then be sort of activated and run as a self-contained environment with all your tools inside of it. And so to return to our portability analogy from the beginning, instead of bringing along like just a camp stove and a pot and our thing of ramen, we're going to bring along like a camper kitchen with us. So why would we want to do this? Why use containers as the way of capturing and moving our software environment rather than these kind of file-based approaches I talked about earlier? So I'd say the main one is just the complexity of the software you're trying to install. Most Python R packages don't need containers. You can create a custom package folder, zip it up, send it with your jobs, no problem. But programs that have a lot of dependencies, need specific versions of underlying libraries or who knows, software that has a lot of components that, so like maybe a bioinformatics tool that uses like 10 other tools, those might be a good fit for containers because it's a good way to kind of capture all that complexity and give you more power in actually installing everything. Along those lines, some software is really particular about where it's installed. So if it must be installed to a system location, that's something you can do in a container. Or if it has to be installed in one place and never move, the container provides that kind of static path that might be needed. Non-technical reason, if you're working with a group of people and you're all using the same software, containers are a great way to make sure everyone has the exact same environment, or pretty close to the exact same environment, because container, you can share the container image, then you can all use that to run your analysis, whatever you're doing. Containers can also run on Linux, Mac, and Windows. So if you want to have the same environment across many different systems, many different computers, can be helpful in that way. Some people use containers for reproducibility as a way to like snapshot or capture the exact configuration or installation they use to run a particular workflow. There's some caveats here. You know, maybe add some comments in the chat if you want to talk about this more. But this can be a reason to use containers. And so those are some of the motivations where you might want to use a container instead of these other approaches. To get started, very similar to the other file-based approaches, you either got to find an existing thing and download it essentially, or make your own, just like you can download code or compile it yourself. So in that sense, you have the same two routes for using containers. And there's two different container implementations, Docker and Singularity. And you can do most things in both. But what it breaks down to is that each implementation has its own image format. So there's Docker images and Singularity images. So that's like the authoritative recipe for the running container, and an engine for actually running the containers that can take the image and like make it into a working environment. So the image format, Docker images can be converted to Singularity images. So a lot of people will, even if they're going to use the Singularity engine, will create a Docker image because you can convert it if you need to. For how the containers are actually run, Singularity is able to run without quite as many administrative permissions. So a lot of shared computing systems prefer that over Docker. Fortunately, it can run both Docker and Singularity images. But so I think you'll see that a lot of people make their images as Docker images, but as they might be used via Singularity. That said, Docker also installs on Linux, Mac, and Windows. So it's also something you can use across different platforms. to actually run containers. Okay, I think that's it. So that's quick intro to containers, what's involved, why you might want to use them. Once you have a container, again, how do we use it in the job? This is going to be different than the previous kind of more file-based approaches we saw. To run a job that's a container, you basically put all the needed information into the submit file. The options are slightly different for using Docker versus a Singularity implementation. So at the Center for High Throughput Computing, we run Docker images directly using the Docker engine. On the OSG, we use Singularity images using the Singularity engine. But hopefully you can see the parallels here. For both, you provide the name of the image. If it's on a lot of Docker images are shared on a public repository called Docker Hub. For Singularity on the OSG, we kind of have our own repository of Singularity images. Requirements. So this is where we're basically saying, in order for this job to run, because it's using a Docker container, I need to run on a computer that has Docker or has Singularity. So those are sort of analogous options. But these are the only options you need to set. There's nothing in your scripts or code that needs to refer to Docker or Singularity. What's going to happen is your script on its own is still the executable. You've given the image information to Condor. And so what it will do is pull the image from wherever was indicated, Docker Hub, a private repository, whatever. It will pull the image to the execute server, start it, and then put your script inside and execute your script. That is all done for you by Condor and how the system is scheduled. So from your perspective, it should look like I'm just running my script on inside this Docker container. So I don't have to make the Docker or Singularity container happen. It's there. My script is inside and it's going to run. So that's kind of how that workflow happens. Okay, so to pull all those pieces together, again, our goal is to run lots of jobs in lots of places. So to use software in a system that's distributed, we don't own, and to use as much of it as possible, we want to make our software portable. How do we do that? We create or find the software we need either as a set of files, a binary, a folder, a container. We either find it or we create it. Once we have that thing, whatever it is, container, tarball, we account for that in our submit file using the either transfer input files, if we have files, using the container image options, if we have a container, any requirements that are needed for our particular code, that all goes in the submit file. And then if our code needs to do some setup, if we need to do some setup on the execute node ourselves, which may be the case if we have like a tarball that we're bringing along or something that needs to be compiled, we can put that information into a script that serves as the job's executable. But that's, again, that wouldn't be needed if you were using a container or a single binary or something where there doesn't need to be any of that setup. Okay, and then this is the acknowledgements. We're funded by NSF. So I'll go back to this slide and leave it up just as kind of a summary, but open it up to a second round of questions.